Hello everyone, hope you are doing well. Welcome to the online platform Civil Techno Bricks. Guys, here we will tune for the instantaneous decoding of conceptual knowledge in the field of civil engineering, where study elaborates decoding the earth to build a better world. Today we will go through the core concepts related to image transformation, image enhancement, and principal component analysis. Image enhancement improves image appearance for visual interpretation, while image transformation creates new information from existing satellite bands. Image enhancement depends on point operations, where a single input raster image is used for pre-processing and post-processing on the basis of some mathematical calculations or process like histogram, where some functions of variable are used to integrate or degrade with reference to the enhancement in the visibility for output image. In transformation, we use multiband operations where n number of multi-layer bands or layers are used as an input with reference to its characteristics. Some mathematical operations are introduced. For example, vegetation purpose, we can use the NDVI indices or vegetative indices so that we get the computed data at the end with reference to some range of colors to fulfill our goal of generation of new physical data through arithmetic calculations. So contrast stretching increases image visibility by expanding pixel values. Multiband transformation combine data from multiple spectral bands using mathematical operations. So in civil engineering, transform images support land use mapping, site selection, and infrastructure planning by providing physically meaningful data. Now, moving towards the principal component analysis point of view, we have some eigenvalues and eigenvectors with reference to the graphical representation of the band A and band B. Band A is of visible red and band B is near infrared. So with reference to the comparison in between them on the basis of eigenvectors and eigenvalues, eigenvectors define the direction of new principal component axis and eigenvalues indicate the amount of variance or information contained in each component. The first principal component PC1 and second principal component is PC2. So we are performing the principal component analysis here. The first principal component captures the maximum information from correlated bands. In civil engineering, the principal component analysis helps identify two important terrain, land cover, and geological features from multispectral imagery. So eigenvectors, the direction of new axis, and eigenvalue, which shows the length of the vector, that is magnitude of variance. So with reference to that variance, we can check the terrain, topography, and many more things so that we plan our analytical approach. The transformation equation based on some principal component analysis, where principal component analysis transforms original satellite bands into new principal components using weighted combinations of pixel values. Eigenvector coefficient acts as weights assigned to each spectral band. Each principal component image is generated from the mathematical combination of original bands. The transformation concentrates useful information into fewer images. So here digital number new is equal to A11 into digital number band A. So A11, A12, A1n are the principal component eigenvectors coefficients. So digital number, the pixel value in the new principal component image. Coefficients A are the eigenvectors that are weights derived from the covariance matrix, and DN band are the original brightness values from the satellite sensors. So every new pixel is simply a weighted sum of the original bands. This is the actual image transformation equation which is followed by the engineers. So civil engineers use just transformed data sets for efficient analysis of transportation corridors, urban growth, and environmental monitoring purposes. So principal component analysis on the basis of covariance matrix. Here we see that the variance, that is the information, and covariance, that is the redundancy. So the two phenomena, information and redundancy, are studied on the basis of variance and covariance technique. The covariance matrix measures how spectral bands vary together. High covariance indicates redundancy, which meaning bands contain similar information. Low or zero covariance indicates unique information from a band. So principal component analysis uses covariance relationships to identify the most informative data patterns. In civil engineering projects, covariance analysis improves interpretation of terrain, land use, and construction site characteristics. So covariance quantifies how much two bands change together. If we have high covariance, then we have high redundancy. And if we have zero coherence, then the data must be unique one. With reference to the feature extraction point of view, we have 2 points: signal versus noise. So principal component analysis separates meaningful information that are signals from unwanted noise in remote sensing data. Principal component 1 usually contains brightness, terrains, and major landscape information. Latter components often contain noise or minor variations. Feature extraction enhances the visibility of important land and surface characteristics. Here, the principal component 1, which shows the brightness and topography, where 97% variance is noted. By using the decorrelated information, we can convert that PC1 to PC2 with some spectral differences based on some feature specific or some characteristics or density point of view. So civil engineering applications includes that slope mapping, watershed analysis, and identification of suitable construction zones for the feature extraction point of view. And we can mark a single feature with a separate color over topographic conditions. Data reduction and intrinsic dimensionality. Now, if we are using n number of layers or characteristics as an input for any process, just like the inputs of 7 Landsat bands, that is the data collected by the Landsat satellite imagery with n number of bands. So, with reference to that, principal component analysis reduces large multispectral datasets into a smaller number of principal components. That is principal component analysis transformation. Most information is retained while redundant data is removed. Data reduction simplifies image processing and analysis. That storage requirements and computational efforts are significantly reduced so that the output 2, which is based on the principal components of 99% information, where noise or any type of redundancy is discarded, and we get a separate and safe output. So in civil engineering point of view, principal component analysis enables efficient handling of large satellite data sets for regional planning and infrastructural management. So intrinsic dimensionality is that reducing file size without losing critical information. Means that data reduction and data dimensionality is the process where we can use data, we can reduce data, but we can't change the actual information enclosed in that data sets. So what are the real world applications of principal component analysis? Principal component analysis supports geological mapping by distinguishing rock and soil types hidden within complex terrain. Change detection helps monitor environment and land use changes over time. Denoising improves image quality by separating useful information from sensor noise. Data compression reduces storage requirements for hyperspectral and multispectral datasets. So separating signals from system noise, which is the most important use of real world application, where civil engineers use these applications for resource assessment, hazard monitoring, urban expansion studies, and infrastructural development. Decorrelation stretch, that is the false color composites, most important phenomenon where standard RGB and PC components. Means decorrelation stretch reduces correlation among spectral bands where principal components are assigned to RGB channels, red, green, blue, that is the color channels, to create enhanced color composites. The technique improves visual distinction between different surface features. Land cover classes become easier to identify and map accurately. Here, the actual satellite imagery of terrain, which is a standard RGB correlated bands, is converted into color composites, that is decorrelated based on some color system, which mapping uncorrelated principal component bands to the RGB creates vibrant distinct color classes. So civil engineer use this for urban planning point of view, mostly construction site assessment and drainage analysis, so that the color guides the civil engineer to take their decision. Enhancement versus transformation. How image enhancement works with reference to the image transformation. So image enhancement modifies existing pixel values primarily for better visual interpretation. Image transformation mathematically combines multiple bands to generate new information. Enhancement is subjective and focuses on image appearance, while transformation is objective and focuses on extracting physical and analytical information. So we are civil engineers, we are using principal component analysis and other transformations which provide reliable data for planning, design, site investigation and decision making in remote sensing and GIS point of view. Stay tuned guys, happy learning.